Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we will extend our discussion on thermal properties of matter. So far we have discussed various basic concepts related to heat, temperature, their interrelationship in the form of specific heat capacity, then molar specific heat, water equivalent. So in this video, we are going to discuss about another important concept, which again is very much related to the field of material science and engineering. Again, the base is thermodynamics, heat and temperature, thermal, science or thermal engineering, whatever you call it, but it has its application in material science and engineering. So it is change of state of a material. Now, we all know that a material, it can exist in three possible states. Okay, whatever the material is, the object is, the substance is, it can exist in three possible states: solid, liquid, and vapor or gas state, gaseous state also they call it. Okay, vapor or gaseous state. These three states are possible. Okay, so how transformation happens or change happens from solid to liquid, liquid to vapor, or in some cases from solid to vapor directly. How does that happen? We will discuss that here. Again, the important thing to understand here is that all of this change of state, it involves heat and temperature. Okay, heat and temperature. Like I said, heat and temperature is the bedrock on which thermal engineering or thermal science or thermodynamics is built. Okay, so whatever you pick, it will ultimately lead you to these two parameters, heat and temperature. Their relationship will be different. The equations may be a bit tweaky here and there, but the base will stay the same. So again, recapitulating something earlier. So heat basically is internal energy because of the molecular movement, and heat transfer takes place between two objects if there is a temperature mismatch between them. One object is at a higher temperature, one object is at a lower temperature, and heat flows from higher temperature to lower temperature till there is thermal equilibrium. That is, TH is equal to TL is equal to equilibrium temperature. Both the temperatures become equal. Then no heat transfer takes place. And another thing, when heat flows out of a body, its temperature decreases, and when heat flows into a body, its temperature increases. But there are some special cases where even if you keep supplying heat, okay, there are some special cases also where if you keep supplying heat, temperature will not increase. It will stay still for a certain period of time. And why? What is that special case? We will discuss it briefly here. We'll touch upon it and then we will expand it in a separate video, because I don't want to mix up these two important concepts. Okay, so you know already about heat capacity. So basically, heat capacity of a particular object or substance is the amount of heat required to raise its temperature by 1 degree Celsius. As it is evident that whenever heat is supplied, there will always be an increase in temperature, as it is evident from this equation. An increase in heat will lead to an increase in temperature. And also specific heat. Specific heat of a substance is the amount of heat required to raise the temperature of a unit mass, that is 1 gram or 1 kilogram of a substance, through 1 degree Celsius. Again here the equation heat is equal to mc delta T. Here it is small c, there it is capital C. Capital C is heat capacity, small c is specific heat. Again here heat and temperature. An increase in heat causes an increase in temperature. This much is clear. So change of state. As I said, matter exists in 3 possible states: solid, liquid and gas. So whenever there is some transformation, there is some change from one state to another through any process, by heating or cooling, by supplying heat or by taking heat out, that is called as change of state of the substance, the transition of a substance or object from one state to another. Okay, so it is very much in you will see it in material science engineering during various applications, during various processes. There will always be transformation of states from one state to another: solid, liquid, gas, and then in reverse also. So it is very much important to understand it. So common change of states, they are solid changing into liquid through heating, that is called as melting of a solid; liquid changing into vapor through heating, that is vaporization of a liquid; liquid changing into solid, it's reverse, okay, through cooling, that is called as freezing of a liquid; and vapor changing into liquid through cooling, that is called as condensation of vapor. So let us try to understand through a very simple experiment using one of the most simplest things which is available, that is water, to understand the change of state of a substance. Let us say we take some ice cubes in a beaker. Okay, we take some ice cubes in a beaker. So we know ice exists at temperature 0 degrees Celsius, but let's say it is a bit lower than that. Okay, a bit lower than that. We will take it slightly lower than that, negative Celsius. So here, let's say we start heating the beaker containing ice on a burner. Okay, we start heating it, the beaker containing ice. So what happens is that as we supply heat, we measure the temperature after every minute. We continuously monitor the temperature and we stir the mixture of ice and water, because as ice starts melting, it turns into water, liquid water. So what you will see is very interesting. Suppose ice is initially at a lower temperature. Okay, here I have taken this XY plot where temperature is in Celsius in the y-axis and time in minutes is in the x-axis. So initially the temperature is at slightly negative degrees Celsius, that is lesser than 0. So what happens, as we start heating it, the temperature, it starts increasing until it reaches 0 degrees Celsius. Here I have mentioned 0 degrees Celsius, but here deliberately I have taken it below, a little bit below that, so that I can make a certain point. So something special happens at 0 degrees Celsius. At 0 degrees Celsius, as you can see, it is being heated. The heat is being continuously supplied, but the temperature is remaining constant at 0 degrees Celsius, remaining still at 0 degrees Celsius without any change for this much interval of time. Okay, the temperature is constant. So here, until the entire ice melts into water, the temperature stays at 0 degree Celsius. Okay, as long as any ice is left in the beaker, the temperature will not change. It is fixed at 0 degrees Celsius. Now this heat which is supplied for this much duration, OA duration time, the heat that is supplied here for OA duration, okay, time duration, that is used up in converting the ice solid into water, liquid, okay, through melting. So this change of state from solid to liquid is called melting at a constant temperature. And similarly, if you do the reverse also, if we reverse it, okay, if we reverse it also, until the entire liquid is converted into ice at 0 degrees Celsius, there will be no change in temperature. That is called as freezing. So that's why 0 degrees Celsius is always taken as reference temperature for design of various thermometers, the lower reference temperature, because of this special property. Okay, so what did you get it from here? That until we reach 0 degrees Celsius and the entire ice is not converted into water, the temperature of this ice, it does not change. Of this ice water mixture, it does not increase, it does not change at all. Same for melting and also for freezing. Okay, now after the entire ice is converted into water, okay, after the entire ice is converted into water, and again we keep on heating it, we keep on continuously supplying heat, then there is rise in temperature. The temperature rises, okay, with time until we reach this point. Okay, let's call it B dash here, until we reach this point. And this temperature is another special temperature, a special reference point, that is 100 degrees Celsius. Okay, that is 100 degrees Celsius. So here what happens, once the water it reaches 100 degrees Celsius, it starts getting converted into vapors. Okay, it starts getting converted into gaseous or vapor state. So as long as the entire water, okay, the entire water at 100 degrees Celsius is not converted into water vapor, the temperature remains the same, that is at 100 degrees Celsius. The temperature does not change. Okay, for this much duration, the temperature does not change. So this much amount of heat from B dash to C dash is used up in changing the state of this water to vapor at constant temperature. This is from solid to liquid, that is ice to water at constant temperature of 0 degrees Celsius, and this is from liquid to vapor, that is water to water vapor at constant temperature of 100 degrees Celsius. So again, that's why this is also chosen as a reference point in thermometers, the upper reference point for the design of thermometers. Okay, so here entirely the water, when the entirety of water gets converted into water vapor, till that the temperature stays at 100 degrees Celsius. Now this change of state from liquid to vapor, that is called as vaporization, and if we do it in reverse, that is condensation also, the same thing will happen. Until the entirety of vapor gets converted into water, the temperature will stay at 100 degrees Celsius. If we do it in reverse also, it will stay the same. This whole thing is reversible. It will follow the same path. So here there are two important things, the two important points. At point O, okay, at point O, both the solid, that is ice and water states, solid and liquid states of the substance, they coexist in thermal equilibrium. Thermal equilibrium means constant temperature, same temperature, no change in temperature. That is called as thermal equilibrium during the change of state from solid to liquid. So at 0 degrees Celsius, both ice and water, they coexist in thermal equilibrium. Now again, at 100 degrees Celsius, both the liquid, that is water, and water vapor, they coexist in thermal equilibrium during the change of state from liquid to vapor at 100 degrees Celsius. That's why these two temperatures are very special in the design of thermometers. That's why they are chosen as reference points, upper and lower reference points. Okay, so now beyond 100 degrees Celsius, if we keep on supplying heat, again temperature rises to CD. So here OA is the melting of ice into water, and BC, it is the vaporization of water into water vapor. These are the two curves. So here we have two important points to specify: melting point and boiling point. So melting point, which is the 0 degrees Celsius point, or it is also called as freezing point if we do it in reverse. So basically it is the temperature at which solid and liquid, in this case ice and water, these two states can coexist in thermal equilibrium with each other. That is called as melting point or freezing point if we do it in reverse. And this characteristic of the substance, it depends on pressure, the atmospheric pressure, so it changes according to that. So the melting point of a substance at standard atmospheric pressure, that is called as its normal melting point. So in this case it is 0 degrees Celsius for water at standard atmospheric pressure. Similarly, boiling point, the temperature at which, in this case, water, that is the liquid, and vapor, that is water vapor, they coexist in thermal equilibrium with each other at constant temperature. That is called as boiling point. Again, the standard boiling point here at standard atmospheric pressure, that is 100 degrees Celsius. And these two are very important in the design of thermometers. Okay, so this is melting and boiling. Now there is another important change also, which I said, where some substance get directly converted or directly transition from solid to vapor state. So this process of transition of a substance from solid state to vapor state directly without passing through the intermediate liquid state, that is called as sublimation, and this substance is said to sublime. Now, common examples of these substances which go through solid to vapor state directly, they are dry ice, which is solid CO, iodine, naphthalene, camphor, and other substances, but these are common. So if you see, when you keep camphor balls in the open for a long period of time, they disappear. They don't melt, it does not get wet there, okay? It directly gets converted into vapor, it disappears into thin air. So that is sublimation, okay? And during the sublimation process, the solid and vapor states, they coexist in thermal equilibrium with each other at one particular temperature. So this is some of the basic changes of state. First, from ice, that is solid, to water at 0 degrees Celsius, where melting and freezing, which are the opposing paths. Then from water to water vapor through vaporization, and in reverse condensation, and in the other case from solid to vapor directly. Okay, now I will briefly touch upon this portion, okay, this portion where the temperature remains constant. I will include it in a special different video to discuss this concept in entirety in itself, because it is a very important concept. So here we know that as per rule of specific heat, any increase in heat will lead to an increase in temperature. Any increase in heat should lead to an increase in temperature. So why at this particular point from O to A, even if we supply heat through the burner, the temperature does not increase and remain constant? And also why at this 100 degrees Celsius point, even if we keep on supplying heat, the temperature does not increase and remains constant at 0 degree Celsius? So this concept, the special concept, is called as the concept of latent heat. So latent means hidden heat. Hidden, because this hidden heat is utilized or absorbed in changing the state from solid to liquid entirely, or liquid to vapor, and also in reverse, liquid to solid or vapor to liquid. Okay, so to entirely change the solid state to liquid, to entirely, so that there is not even a shred of solid substance left, we have to supply some extra amount of heat which does not contribute to the change in temperature, and that is called as latent heat, hidden heat. This is called as latent heat of fusion for solid liquid transition or liquid solid transition in reverse, and for liquid vapor transition it is called as latent heat of vaporization. Now we will discuss it in a separate video in detail. For now you just understand that this is the concept of latent or hidden heat, okay, where this extra heat is utilized in changing the state from solid to liquid, where it is called as latent heat of fusion, and solid to liquid or liquid to solid, and the other case where it is latent heat of vaporization from liquid to vapor or vapor to liquid in reverse. And this happens all at constant temperature, thermal equilibrium. Okay, so this is the basic concepts related to change of states, and This is the thing. Okay, so I used this basic simple experiment so that you can understand it in a better way. For different substances, these latent heats, these reference points, these constant temperature points, these plots, it will be different in nature. This is for ice, water, vapor, transition. Ice, water, vapor. For other substances, it will be different, but the basic crux, the basic foundation will always stay the same. For other substances, this 0 degree Celsius point will be somewhere different. This, vapor state, liquid vapor transition point will be a bit different. Okay, so these solid liquid and liquid vapor transition points or latent heat points, latent temperature points, it will be different, but the basic structure will be the same. They will go through the same, the journey will be the same. The checkpoints will be at different places for different substances, if you can get my analogy here. Okay, for some it may be lower, for some it may be higher, for some it may be lesser than 0 degrees Celsius or greater than 0 degrees Celsius. For some it may be lesser than 100 degrees Celsius or greater than 100 degrees Celsius. But they will go through these same states. The structure, the overall journey, the pattern of the journey will be the same. Okay, so this is the thing.